right. Hello, this is Mr. Dermott. I'm here for our review for the functions test coming up. It's been a whirlwind of a week working with functions, and this is going to be a test that is very much yes, no. You're going to be kind of going through these questions pretty quickly. There's 60 questions on the test, but most of these questions are just going to take you a matter of seconds. All right, so let's jump right in. And these are some of the quick questions. So these are all questions about whether it's a function or not a function. So the big rule that you need to remember when you're dealing with a situation with ordered pairs or with a table like this one is you're just looking to see if any x values are repeated, right? So we've got a bunch of x values here. Just looking to see if any x values are repeated. So in this case, our x values are -7, -3, 5, and 6. None of them are repeated. X values are not repeated, then it is a function. Notice here that we have some y values that are repeated, right? So 2 is repeated there. -2 is repeated there. But that does not prevent it from being a function. Y values can be repeated, but x values cannot be repeated. Functions cannot repeat x values. So this example for number 1 is a function. This example for number 2 is not, because as we're looking at number 2, take a look there. We've got that x value of 200 and that x value of 200. We have x values repeated, and therefore that is not a function. All right. Let's look at a couple more examples like this. Skip down to number 6, and you're going to see that we're kind of dealing with the same kind of problem. We're just looking for, we're scanning these x values right here, and we see that none of them are repeated, right? We do have repeated y values. We have a repeated y there, but that doesn't matter. Repeated y's are fine. This is a function. As we go all the way down here to the bottom of the page, look at this table right here. On this table, we have a bunch of repeated x values, right? So 4 is repeated, 6 is repeated, 8, 6, they're all repeated. So this is not a function. So in situations where you're given x and y values either through a series of ordered pairs or through a table, you're just looking for repeated x values. Now, we're also going to be getting graphs. And the trick with graphs is the vertical line test. All right. And so the vertical line test is just looking at a given graph and asking, hey, if I was to draw an up and down, a vertical line at any given place through this graph, right? Can I find a place where that vertical line would cross through the graph more than once? So like in this case, I could do a vertical line anywhere, and it's only going to cross through once on any given location that I draw a vertical line. So that would be a function. Likewise, when we look at number 3, this horizontal line, this is going to pass the vertical line test anywhere we draw a vertical line. So this is a function. Number 4, likewise, is a function because it's going to pass a vertical line test wherever I try to draw that vertical line. Okay, I'm going to skip number 5 for just a second. And I'm going to actually jump all the way down to number 14 on this page, right? Look at number 14, this circle, all right? So if you were to graph a circle is not a function. Because if I draw that vertical line right there, you're going to see that it crosses there and it crosses there. The vertical line crosses in 2 places, so that is in F. That's not a function. And then let's just look at a special case. Look at this horizontal line right here, all right? A horizontal line is going to, let's think about if I drew a vertical line on top of that horizontal line. It's going to fail the vertical line test because that vertical line on top of a vertical line is going to intersect it at every single point into infinity. So this is, horizontal lines are not functions. all right? Another special case is where we're dealing with non-continuous lines. Notice that this one has an open circle, then there's a closed circle down here. When we're looking, that these circles would be the only place that they would overlap, right? But notice, just like when we're graphing on an inequality, when we're graphing solutions to inequalities, right? Remember that this one included that point. This one, the darkened one, includes that point. This one does not. If you have a situation where you've got an open point on top and a closed point below, and they go through the same vertical line, this is a function because there's actually only one point that we count there. We're saying that this line up here may start at that point, but it doesn't include that point. This line down here starts at this point and includes it. If we have something like this, then we would say that that is not a function because this line up top starts at this point and includes that point. This line on the bottom starts at that point and also includes that point. And there is overlap in that one single point, all right? Okay, so this example right here would be a function because it was an open circle and a closed circle. We just said that if we get a vertical line like this, it's not a function. These two examples, I just want to remind us of something that we learned back when we were graphing. We learned this a mnemonic that we called Vux Hoy, and it's two special kinds of graphs that we do, okay? So when we get a graph that is x equals a number, then that's a Vux graph, okay? When we say Vux, what we mean is it's a vertical line, right? It's vertical, and that slope is undefined, and it's x equals something. So that's a Vux graph. And then we had these Hoy graphs, right? And that's y equals a number. The slope is zero slope, and the h is for horizontal, right? And so that line just looks like that. When we have our Vux lines, our x equals something, then that is going to be not a function, all right? Because vertical lines are never functions. When we have a Hoy line, one of our horizontal lines that's y equals something, then that is always going to be a function, okay? And so that applies directly to number 8 and 9. You're going to see questions on this test tomorrow where you have like this one, y equals 18 minus 20. Well, it's not just y equals a number, I know, but we can simplify that down to y equals a number, right? We know that that would end up being y equals -2. That is y equals a number. That's a horizontal line, all right? So for that reason, we'd say that that one is a function. And when we have this kind of lengthy equation where we're solving for x, if we were to solve for x, we'd eventually get to a point where it would be x equals, I'm trying to do the math in my head, I think it would actually be x equals -1 if we go through all the steps to solve it. And that would just be a vertical line, right? That would be one of our Vux examples, a vertical line. And that is not a function, all right? So just those two special cases we want to be aware of. Another special case is our f of x. This is, if you'll remember from class, we call this a function notation. And as the name implies, function notation, anytime you have something in function notation, it's always going to be a function, okay? So just be aware on the test if you see something that's in function notation, it's going to be a function. If it's just a question, is this a function or not? Well, yes, it's in function notation. One of the, for us, more challenging topics that we covered was mapping functions, right? So when we map, we have all of our domain values circled up from least to greatest on the left, And then we have all of our range values circled up from least to greatest on the bottom, and we map them. And when I say map them, what I'm saying is that for 5, this line that connects to 1 tells us that one of the ordered pairs in this function is -5, 1. We kind of continue and figure out our next order pair. All right, well, there's a connection from -5 to 2. So it tells us that another ordered pair within this function is -5, 2. Another ordered pair would be -2, 3, 0, 3, and 1, 4. Those are all of the ordered pairs in the function that we have mapped right there. And just notice that we have a set of repeated x values, and so this is not a function. The thing I want you to pay attention to that you can recognize visually really quickly without even going to the trouble of doing this is if you see this less than sign, okay, you see that sign in a mapping, then that's going to not be a function, okay? I want to point out that we can have this right here, and this kind of looks like a greater than sign for lack of a better term. And we can have 2 items in the domain that are mapped to a single item in the range, and that would end up just looking, if I was to write those ordered pairs for this one, it would be A, E, B, E, C, F, and D, G, right? So those would be our ordered pairs. And just notice that as I look through my x values, I don't have any repeated x values, and so that is a function, all right? We already talked about number 14, clearly fails the vertical line test. Look at number 15. We talked about these closed circles. If I was assuming these are right on top of each other, I did just sketch these out, but assuming they're right on top of each other, then this point is included, this point is included because they're both colored in. So this would fail the vertical line test, so this would be not a function, okay? So that's a big chunk of this test, is just identifying whether something is a function or not a function, given those types of examples. Another part of the test is going to be identifying linear versus nonlinear relations, okay? So basically, for a relation to be linear, you need to have no exponent on either of the variables. Variables cannot be in the denominator. You can only have, you can't have more than 2 variables. Can't have absolute value, and you can't have the variables inside absolute value or under a radical. So let me just kind of show you what that looks like. So this one right here is linear, right? That's an old school y equals mx plus b equation. We should know immediately that that's going to end up graphing a straight line like that. For number 2, this is nonlinear. All right, and the reason is because we have these absolute value signs right here. You're going to have to explain how you know it's nonlinear, and the way that you could explain this is just to show me that you've got x in an absolute value. If you want to write out the words, x is inside absolute value, that's fine too. I would want to write less personally. And so that's not linear, and that's going to give us a graph that looks kind of like that, right? And we can all identify that's not a straight line. For number 3, this is also nonlinear, and the reason that this one is nonlinear is because right here we have a variable that's included under this cube root sign. So if you have a variable inside of a cube root, a square root, any kind of a root, it's also not going to be linear. And all you got to do to show me that, like here, if you just showed me that, then I would say, okay, you understand that the reason is because the variable is under the root sign. Number 4 is a tricky one, and number 4 is meant to be tricky because, you know, there's a bunch of expressions here, a bunch of parenthetical expressions. Looks like it maybe is something going on more than a linear equation, but this is actually also linear because we can distribute this 3, this 2, and this 3, and our outcome is going to be still variables that do not have an exponent. None of these variables are going to be in the denominator. We don't have a variable being multiplied by another variable. We don't have any absolute values. We don't have any roots. And for that reason, this is going to be a linear. All right. For number 5, this is going to be a nonlinear. And the reason that number 5 is nonlinear is because when I multiply 2y by x, well, right here, we've got a variable being multiplied by a variable. And you could just show me that by variable times variable. Or if you just wanted to copy down the equation that makes it nonlinear, then that's fine too. But really it's because we're multiplying a variable by a variable. And then if we solve that, we would end up with a variable in the denominator. But this is nonlinear. Looking at number 6, this is nonlinear because if you look, we have 3 different variables. Now I want to point out, like looking back at number 4, we have a bunch of variable terms, right? We have 1, 2, 3, 4, 5, 6 variable terms, but there's only 2 variables. There's only an x and a y, right? Here we have 3 different variables, an x, a y, and a z. And then anytime that we have 3 or more variables, that is something that will make it nonlinear. Number 5, looking at number 5, this is a tricky one as well because I've got 5 squared here. And if y'all remember, in instances where we have a variable with a square or a variable with an exponent, then that is nonlinear. But this is not a variable with an exponent. That's just 5 squared. That's 25, right? That's going to simplify down to 25y equals negative 3x plus 2y. And here, this is clearly linear. So this is linear. But again, if you had x squared or, if you had something like y equals x squared plus 2x plus 1, something like that, you've got that variable that exponent attached to a variable. That is what makes it nonlinear, but this one doesn't have any of that. It's linear. Number 8, we've joked around about pi being nothing but a number, and it is. So this is really the same thing as y equals 3.14 times x, and you're doing that does not prevent it from being linear. All right, so this is, if you see pi alone is not a reason to say it's nonlinear, so this is linear. Okay, number 9 and 10, this is a kind of newer idea for us, and we practiced it some today, but you may want to just get this refresher tonight. So as we're looking at number 9 and 10, if you're given a collection of ordered pairs, you can find out if those ordered pairs are linear or not linear in their relationship. And the way that you do it is step number 1 is you order them by domain from least to greatest, right? So you list them by x value least to greatest, right? So here's what I'm going to start with 0, 5. These are my x's, these are my y's. 0, 5, 3, 6, 9, 8, 27, 14. And then all you're doing is you're calculating the slope for each set of ordered pairs. So we're going to look at what the slope is from that ordered pair to that ordered pair. So as we look at the slope for between each ordered pair, what we're looking to see is if the slope is constant, right? Does the slope change? If the slope is constant, then it's linear. So here's how we do this. Slope, if you'll remember, is change in y over change in x, right? So our change in y is we start with 5, we get to 6, that's plus 1. We start at 0, we get to 3, that's plus 3. So my slope here is going to be 1 over 3, okay? Let's look at my next jump, right? From this ordered pair, 3, 6 to 9, 8. So I start with 6, I end at 8. This would be a jump of 2. I start with 3 and I get to 9. That's going to be a jump of plus 6. So my slope here is going to be 2 over 6, but I know that 2 over 6 is the same as 1 over 3, right? We can reduce that down. So the slope is consistent from the first set of ordered pairs to the second set of ordered pairs. You have to test all of them, all right? So looking at the last set of ordered pairs, I start with 8 and I get to 14. That's going to be an increase of 6. If I start at 9 and I get to 27, that's going to be an increase of 18, right? So 6 over 18, I can reduce that down also to 1 over 3, right? Because I can divide 6 and 18 by 6 and I get 1/3. So here, 1/3, 1/3, 1/3. The slope between each of these ordered pairs is 1 up and 3 to the right. And for that reason, they end up being linear, okay? Now look at this second example. Now I will admit I wrote this out by hand as a test review. I should have put these in order from least to greatest. So I'm just gonna scratch that out and do that here, okay? So this should be 4, this should be 6. And they'll be in order on your test, 2 and 0. So let's do the same thing here, all right? So these are our x's, these are our y's. I start with 5, I get to 2. That's a decrease of 3. I start with 0, I get to 4. That's an increase of 4. So my first slope between this first point to the second point is negative 3 over 4, okay? So let's now check from this point to this point. Start with 2, I go to 0. That's a change of negative 2. I start with 4, I get to 6. That's a change of positive 2. So this slope is negative 2 over 2. All right. Notice that these are not the same. These are different, right? That tells us that the slope changes, which tells us that it's not a straight line. I'll kind of show you what it might look like by just sketching it out. But let's look at this last ordered pair. Start with 6, 0, go to 8, 4. My 0 goes to 4. That's a change of plus 4. 6 goes to 8. That's a change of plus 2. And so that is going to be, that's going to get me to 2 over 1. So really this line would end up kind of looking like this. So between my first 2 points, it's going to look like that. Between my second 2 points, it's going to look like that. And then between my third 2 points, it's going to look like that. And, you know, y'all, you can look at that and you know that's not linear, right? So non-linear. Now, that is a lot of work, and I'm aware of that. And just, I'll tell you now that there's only maybe 1 or 2 questions on a 60-question test that involve this. So it's not going to kill you, but it's something that, you know, I know that many of you are shooting for hundreds, and so want to encourage you to get that right. Okay. Function notation. Function notation. All right. So for function notation, all that you're doing is, again, we said that f of x is the same thing as y, right? With function notation, the way we read this is f of x equals x to the third power plus x squared. With function notation, when it says find f of 2, remember that 2 is where x was before, right? So what we're doing is we're subbing in 2 for x. So when I sub in that 2 for x, I end up getting 2 to the third power plus, I'm subbing in for that x now, 2 to the second power, all right? So I can find f of x, which really means just y, when x is, f of 2 is this, right? So 2 to the third power is 2 times 2 times 2, which is going to be 8, plus 2 to the second power is 2 times 2 plus 4. In this case, that would end up being 12. So f of 2 is 12 in that case. Function notation is, it looks complicated, but it really is not that bad, right? Let's look at this next one, all right? Notice that this one says r of x. It doesn't matter. R of x, f of x, b of x, a of x. It doesn't matter. So here we're looking for finding r of 9, right? So r of 9 equals, well, I'm just subbing in 9 wherever I had x before. So I've got 4 times 9 squared plus 2 times 9, all right? So 9 squared is 81. I'm going to multiply that by 4. 2 times 9 is 18. 4 times 81 is 324 plus 18, and that's going to be 342, right? So R of 9 equals 342. All right, so that's how you're going to solve those. And again, there's, I think, one question on this on the test. Okay. Okay, so let's talk about domain and range really quick. So domain and range, here's the deal on these. Okay, so with domain and range, all we care about is what X values or what Y values you could have. So again, remember that domain is possible X values, and then range is possible Y values, right? So let's look at the X and Y values of each of these points. So this one is -1, 2, 3. So this is -3, 1. This is -3, -3. This is -1, -2. This is 1, 4. This is 3, 2. And this is 5, 6. All right. So if I'm asking for the domain of these, I'm just listing all of the X values, right? All the potential X values. So here, both of these guys have the same X value of -3. So my first domain value is -3. My next one, well, there's my X value, -1. My next one is 1. My next one is 3. My next one is 5. And it's one of those things where, like, just don't overthink it. It is not, domain is X, right? Range is just Y, right? So what are my possible Y values? So let's look here. Here's my first one. Y is -3, right? Because it hits right here on the Y axis. My next one is -2. My next one is, what's this one? A lot of people would say -3. No. My Y value there is, my Y value there is 1. My Y value there is 2. The only thing you can mess up here is getting your X and Y mixed up. My Y value there is, oh, look, I already did that. I included that as one of my Y values. Oh, no, I did right, because this Y value is 1, that Y value is 2, that Y value is 4, and that Y value is 6. You only list them one time, by the way, all right? So I have 1, 2, 3, 4, 5, 6 members of the range set, and I have 1, 2, 3, 4, 5 members of the domain set. The reason I only have 5 members of the domain set is because, look here, both this point and this point share the same domain value, the same X value of -3, okay? So it gets a little bit more complicated when we start looking at continuous graphs that include lines, all right? But it's still not bad. Let's just think about, again, domain and range. I like to think about like how we're blocking it in, okay? So as I look at this line, when I'm looking at the domain, look at look how I'm blocking this in, right? My potential X values, I've got no potential X values over here. X is never going to be less than, what is this? 1, 2, 3, than -4, right? X is never going to be less than -4. But then I look here and I'm also blocked in over here for my X values, right? X is also never going to be more than -1, okay? So really all of my X values are going to be encompassed in that little swath right there. So the way that I express this mathematically is I just set my limits. -4 is one limit, right? And then -1 is the other limit. And then my value, X, is what's in between. Now, this is a closed circle, all right? X is going to be greater than -4. Well, guys, I mean, just think about your inequalities, right? The alligator points to the greater number. X is greater than -4. I know that we might read this as -4 is less than X, but just know this is the same as X is greater than -4. But it's not that X is greater than -4. It's a closed dot, so X can include -4. So I write my greater than or equal to sign. Likewise, X is never going to be greater than -1. X is always going to be less than -1. All right, so I put my less than sign. This is that kind of double inequality. And the reason it's just less than is because I have that open circle. All right, that open circle means that it does not include -1. All right, so it's just less than -1. And that's how it express that domain. I could do the same thing with the range, right? Think about where we're boxed in if we're looking at our up and down, right? The highest value that I'm ever going to have for y is going to be 5. The lowest value that I'm going to ever have for y is just over 2, right? So when I talk about y, I start at 2, I go up to 5, y is in the middle, y is going to be greater than 2, it's going to be less than or equal to, because it's a closed dot, to 5, all right? This is domain and range on continuous graphs. Let's look at a couple other examples. Let's look at the domain of this guy right here, right? So the domain, we're looking at how far we go down go across the x-axis. So my lower end is -1, 2, 3, 4, 5. So my lower end for domain is -5. X is going to be between -5 and what number? +2. All right. So we know X has got to be, X is not going to be less. X is going to be greater than -5, greater than or equal to. And then it's got to be less, right? Less than -2. We're not going to have any y value on this side because our graph is over right there. There's no more data on that side. So X is going to be less than, and it's less than or equal to because it's a closed circle. Less than or equal to -2. So that's our domain on this one. Let's look at our range on this guy up here really quick, okay? So range on this guy, let's think about our lowest end of the range. Is it this one? No. It's this one right here, right? So we don't have any values that are lower than 2, right? All our values are up above that, right, including that. So it starts at 2, and it goes all the way up to this guy up here, which is 3, 4, 5, 6, 7, 8. And what variable do we put in the middle? We're talking about our up and down. This is our y-axis, so it's our y values with range. The low, and it's a closed circle, right? So it's going to be y is greater than or equal to 2. Closed circle up here. Y is greater than y is less than or equal to 8. And I know that we've got these 2 points right here in the middle, but these points actually don't even really matter for this as we're just looking at the scope of the range and domain, because it's just, are there values included? Are there y values? Where do we have y values included? And it's in this swath right here. Likewise, if we looked at x's, where do we have x values included? Well, starting here, we got x values all the way up to up here, right? So this is domain and range. We do look at domain and range on some continuous graphs, right? On some graphs with arrows on them that go into infinity, all right? So anytime you're dealing with a graph that has an arrow on it, you need to look at the direction of that arrow. If there is any upward tilt at all, or any sideways tilt at all, this graph is going to go into infinity in that direction and, right, on the x-axis positive, and it's going to go into infinity because it keeps on creeping up on the y-axis. Likewise, on this side, it's going to continue to hit y values negative because it's going down at an angle. But it's not just going down at an angle, it's going to the left. It's going negative on the x-axis at an angle. So this graph has a domain and a range. The domain, the side to side, it's going to be all real numbers. And the range, the up and down, it's actually going to also include all real numbers. I'm going to come back to this guy right here in 1 second, but I just want to look at this, this parabola here and kind of talk about this case. This is a special shape in math, and I've not drawn it particularly well, but what I want you to see is that these arms right here, they kind of creep out at an angle if you look. Because they go on to forever and they're always creeping out, they're eventually going to hit all of the x values in that direction over time eventually, right? And all of the x values in the negative direction as well. So the domain of that parabola is going to be all real numbers, right? And then the range, obviously in the upward direction, it's going to go sky high. It's never going to stop increasing, but it does have a starting point, right? If we look at it here, there are no y values below this little rumpus, below this little lower limit of the parabola. So we can look at this as a starting point, right? So it's going to start at 1, and then it's just going to continue going forever. So basically what we're going to say is that y is greater than 1. And it's actually greater than, and I drew this dark dot there so I can make it clear, it's greater than or equal to 1. And so that's the range of this parabola, right? Sometimes you'll have parabolas that might be pointed to the side like that. It's going to have the same domain and range as this guy right here. So again, look. This guy creeps out, right? Creeps up and down, and it shoots out to the side. So here, my range is going to go on forever and ever, right? My range is going to be all real numbers. And then my domain is going to be, it's going to go on indefinitely, infinitely to the right, but it's going to start here. There's no domain values that are lower than, in this case, you see I was funky. I said that the first tick was 5. I went 5, 10, 15, 20. So really here, the domain starts at 5 and then continues up. So x is any number greater than or equal to 5 for the domain for that. All right. Lastly, just make sure that as you're looking at these, if there is not an arrow, which there's not on this one, it doesn't go on forever. It stops here, okay? So this would be a limited range. So the range on this one, -2, -4, so the domain here would be -4, and the domain goes up to 8, 10, 12, 14. And then, so x would be greater than or equal, less than or equal to that. So that would be the domain for that. And likewise with the range, right? With this one, this would not be the bottom of the range. The bottom of the range would actually be that point right there, which I think is 2, right? So the range there would be 2, and then it goes up to 8, 10, 12, I think it looks like 14. So the y is greater or equal to that. And that's kind of how we'd express that range, okay? Look, there's a bunch of definitions, not a bunch, 7 definitions that are going to be on the test. They're written exactly as this, incidentally. There is no word bank for this, but this is totally doable for y'all. When we talk about a set of ordered pairs, that's just a relation, all right? Some relations are functions, some are not. By the way, like sometimes just notice that the answer, the word bank sometimes is in the set of questions farther down. A special type of relations that do not repeat, those are functions, which by the way, there's that word if you need it. Number 3, the inputs are x values of a function. Those are the domains. That's the domain. The outputs are y values. That's the range. You just got to know these. Whenever we're using f of x or g of x or whatever of x, we're talking about function notation. When we're talking about linearity, the graph of a straight line is obviously linear. A graph of a line that's not straight is nonlinear. These are freebies. Testing solutions. All right, so when we test solutions, when we get a function you might get an ordered pair, and the question might be asked, hey, is this ordered pair included in that function? Well, the way you find it is by plugging it in. So in this case, remember f of x, you can just treat that like y, okay? So the way that I would test it is I would plug in f of x. I'd just plug in my y here for that. -1 equals 2/5 times 9 minus 5. All right, now y'all, these are some ugly fractions. You're not going to get fractions like this on the test, but you can do it. You can do hard things. So 2/5 times 9 is 18. 18/5 minus 5. Okay, and then 18/5 is 3 and 2/5, negative 3 and 2/5. Minus 5. I'm sorry, that's not -3, that's positive. I don't know how I did that. I'm tripping today. And then if I subtract 3 and 2/5, if I subtract 5 from 3 and 2/5, I'm going to get 1 and 3/5, which is not a beautiful fraction. It's going to be negative. But you get down to this, and you've got a number equals a number. Look, -1 is not -1 and 3/5. This number does not equal that number. When you're testing a solution, when you plug it in, if you get a number and another number on the other side of that equal sign and they're not equal, then this is not a solution. Okay, let's look at an example that, spoiler alert, is a solution. Okay, so here we've got our x value here and our y value here. So y equals, remember, this is the same as that f of x thing. I just want to draw your attention again to the fact that it might be written as f of x, it might be written as y. It is the same thing essentially. So let's plug it in. So we've got -6 equals x squared. So that's -1 squared plus 2 times -1. Just plugging in my x value wherever it occurs, minus 5. Okay, so -1 squared, -1 times -1, and negative times negative is a positive. That's going to be +1. Negative times, positive times a negative is a negative, so that's going to be -2 minus 5 equals -6. All right, so -1, +1 minus 2 is going to be -1 minus 5. We're going to have -6 equals -6. And y'all, -6 does equal -6. And because they equal each other, and it makes sense, it's not a glitch, then we're going to say that yes, it is. Yes, it is a solution. All right. And so that is it. I apologize for getting this out late. I recorded this whole video at school, and unfortunately, it did not save on my Loom account. So I'm looking for other options. Appreciate your time. I wish everyone luck on this test tomorrow. I feel like you'll be prepared.